We will conclude this chapter by basically mentioning ocean eddies. We won't do much with it. We have already seen that atmosphere has lots of mid-latitude eddies, and ocean also has lots of eddies everywhere. And we'll see the simulation from NASA that we saw before here again. So here is a map estimating the drifter speeds in terms of eddies. What do we mean by eddies? We had kind of mentioned the variance of the sea level before. So if sea level is varying in x, y, and time, then it has a long-term mean in space plus a time variation around it. So the variance is basically square root of that n squared average over time. What does that give us? Basically, that tells us this is what we had seen before. Mean surface current speeds and variance here, which is estimated as u bar squared plus v bar squared to the 1/2 square root of that. So eddies are anything that are swirling, so it can be deviations from the spatial mean or deviations from the temporal mean. This eta bar xy here is the long-term time mean of sea level, and eta bar is the time deviation. So there are these wiggles in time that can be considered eddies, right? We know we will see what we mean by that. So we said the scale of the eddies depends on the Rossby radius, and Rossby radius has f in the denominator, so obviously near the equator you can get into trouble, but there are dynamic constraints near the equator, but also f in the denominator means that the Rossby radius decreases as you go to higher latitudes because f increases. So the scale of the eddies can decrease with latitude as well. Why are they important? If eddies in fact have a role to play in let's say mixed layer physics or transporting heat and so on, then they must be represented in models, which means when the models create grids, the grids may have to be small enough to capture the eddies explicitly, which means they have to be smaller than the Rossby radius of deformation, which means large computational cost, and so on and so forth. So eddies have lots of important physical importance and can create problems for modeling. So here is a instantaneous map of surface current speed from a global eddy resolving numerical ocean circulation model. We'll see one we had seen before again. This is from JPL people, and they run very high resolution model, which means the grid resolution of the model is much higher than, or at least similar to the scale of the eddies or the Rossby radius of deformation. That's why they're called eddy resolving. They are small enough to actually capture eddies. And you can see the cute features here. So here we are with the Kuroshio, and the extension goes wobbly. Those are all eddies, but there are also eddies all over the place. There are waves in the deep tropics that are related to instabilities in the currents. Horizontal shear can split into eddies, just like we saw in the mid-latitude atmosphere, where we said angular momentum created baroclinic instabilities which broke into eddies. There was a spontaneous instability of the zonal jet, and so on and so forth, right? And the rings also get shed here as the western boundary currents want to go across this along this sloping coastline. So this can also induce some interactions with the changing Coriolis effect with latitude and shed rings. And then within the Gulf Stream, within the Gulf of Mexico, you end up creating what are called loop current eddies. Then Gulf Stream comes off here and also creates eddies. When you look more specifically at a temperature map for June 20th, 2003, very close to the June 21 we had been looking at for the atmosphere. You can see the closely packed sea surface temperature contours here, but you see that there are these trapped eddies. So as the Gulf Stream meanders, this is called a meandering, it can shed a cold water eddy on this side and a warm water eddy on the other side, and these eddies can hang around for months. Oftentimes fish get stuck in them and they're happy to feed along, and the fishermen know it and they try to chase the eddies and catch the fish and so on and so forth. And it turns out that these sharp fronts also have an atmospheric response. For example, by hydrostatic balance, warm temperatures will have low pressure, cold temperatures will have high pressure, and you create a pressure gradient and some local circulation when you have very sharp gradients, and so on. And here is an example in the Southern Ocean where the trajectory of a surface drifter made 1.5 loops around Antarctica between March 95 and March 2000. So it took exactly about 5 years to make this 1.5 loop. So why does it take so long? If you just look at the mean currents, it shouldn't take that long at all. But the drifter gets trapped in eddies and keeps circulating and then gets out and then makes some progress, gets trapped again. So the time is here very much related to getting stuck in the eddies and not just drifting along with the mean currents. In fact, in this region, it doesn't make much sense to say mean currents because they are mostly eddies. So let's look at that perpetual ocean again for a moment just to remind ourselves if this will open. Yes, it does. This has music, so but it's turned off, so I can speak. This is again from NASA, the same eddy resolving model kind of simulation. Now there are many fantastic simulations from GFDL, NOAA's National Ocean and Atmospheric Administration's Geophysical Fluid Dynamics Lab in Princeton, New Jersey. And you can see the rings we were talking about the North Brazil current going into the Gulf of Mexico, loop currents, lots of eddies here, lots of instability waves here, Agulhas outflow and the Agulhas retroflexion creating all these meanders and eddies. Indian Ocean, the Somali current that crosses the equator here also goes unstable and creates lots of eddies. There are lots of beautiful theories which will tell you that when low latitude strong currents like this cross the equator, vorticity changes end up creating nonlinearities and shedding eddies. This is the South China Sea with Luzon Strait and lots of eddies around in this region as well. There is our Kuroshio with lots of its extension and eddies, and then can clearly see eddies tripping off here into cold eddies, on the other side into warm eddies. I think it'll zoom down to the Southern Ocean in a minute. There are loop currents in the Gulf of Mexico, lots of eddies coming off here. If I can jump forward to the Southern Ocean, there we are with the Antarctica, and you can see that these currents are not steady at all. They are always full of eddies. Okay, so drifters launched here keep getting stuck into eddies and then making progress very slowly around. But if you average over a long time, obviously you will get very, very strong currents. And the main thing to remember again is that the Southern Ocean is a channel, so it has this beautiful wind forcing that can put much more energy into it than in the other oceans where boundaries limit the amount of energy you can put in. So if I have to go back to my PowerPoint, then I have to do this. So that's the end of this chapter. The next chapter is on ocean circulation with more dynamics, showing the western boundary intensification, going back to our equations and seeing why western boundary intensification happens. It's one of the more elegant ocean solutions. Okay.